P.7 is our last section in Chapter P, the review chapter for our textbook, and it is titled Complex Numbers. I have alluded to this on 2 occasions at least that I can remember so far, and so we're here finally. The first thing I'd like for us to do is to define what a complex number is. Complex numbers are numbers with the form a plus bi, where a and b are real numbers, and I is the imaginary number. By definition, I is equal to the square root of negative 1. Or you can define it that I squared is equal to 1. So some identification first. We're just deciding if the numbers are real or if they are imaginary. So, and then we'll do the complex form in just a second. The first number, negative 72, real or imaginary? Real. The second one, negative I squared 5, real or imaginary? Imaginary. And you're all thinking, can every problem look like that? Right? Those are fast. Right? All right. Complex number form, this a plus bi form. Notice up here in this description of a plus bi that nothing in that description actually said that a and b can't be 0. Right? And if it's never said, then it means they can. That's really what it means. If a is not, unless it says it can't, it can. So as I'm looking at negative 72, and if I want to write it in this complex form, it's negative 72 plus 0i. Now, I may feel silly to do that, but what I want you to recognize in doing that is that the number negative 72 is a complex number. It just has a 0 coefficient on its imaginary unit. But it's a complex number. Same thing's true for the other one. On this one, I have negative square root 5i. Was it negative? Yes. And so it's missing the real component a at the beginning, so it's understood to be a 0. So that's fine. Put the real component first, may or may not be 0. You put your imaginary component with its coefficient second. That component's coefficient may or may not be 0. That's complex form. Adding, subtracting, and mostly multiplying with imaginary units feels very much like doing it with polynomials. Addition and subtraction, it feels exactly the same. So we're working with like terms, just like we were with polynomials. If something has an x in it and something else has an x in it, and they both have exponents of 1, they're like terms. Same thing for i's. So as I look at this one, I have an addition problem on number 3. And I just pair up the pieces that are alike. I have negative 3 and I have positive 5, and I can add them together and I will get 2. Then 2i and the negative 6i are like terms because they both have the I attached to them. So what is positive 2i and negative 6i? Negative 4i. Addition, just like with polynomials. No different. Subtraction, same thing. I do need to be careful, as always with subtraction, that I make sure to distribute the negative. So if you can do it without actually writing it down, more power to you. I always write mine down because I tend to lose negatives. That's something that I tend to they get distracted. I don't know. So I'm going to write mine down. I have that same 6 minus 7i at the beginning. So again, combining like terms. 6 and negative 3 gives me 3. Negative 7i and positive 4i gives me negative 3i. Just like with polynomials. Multiplication starts out just like with polynomials, but it has a twist at the end. So we're going to do the starting out just like polynomials. I have 2 binomial expressions here. I'm going to distribute them out, FOIL them out, whatever language you like. I like FOIL, so I'm going to do first 3 times 5, 15. Outer, 3 times negative 2i is negative 6i. Finish for me. What's negative I times 5? Negative 5i. And then the last one is negative I times negative 2i. Yep, positive 2i squared. Okay. The negative 6i and the negative 5i clearly combine, just like with polynomials. What is negative 6i minus 5i? Yep, negative 11i. And this 2 is 2. I'm sorry, I left it off. I squared. The I squared, however, at the end has a value. What is I squared? Negative 1, and that's our twist, right? Anytime I see powers of I cannot leave them. So this is negative 1. Now, do you have to write it that way? No. If you see that you have 2i squared and you just change it to negative 2, that's fine. I mean, that's what's going to happen here, right? I'm going to have 15 minus 11i, and I'm going to have minus 2. And I have one more piece where I can combine these two together. The 15 and the negative 2 is going to give me 13 minus 11i. Now, I said it, but I haven't shown it. But every problem that you deal with complex numbers will always have, at most, the real unit, the imaginary unit, and no other powers of I, ever. So we'll talk more, and I don't think we'll get to it today, but we will talk more about what happens if it had been I cubed or I to the 5th. What happens when those kinds of things come up? So we'll get there, but just know your answers will always be in that same complex number form, A plus BI. Every time, A plus BI is the form. Number 6 actually does not feel like things that we have seen with polynomials, but it does feel like things we saw with radicals. Now, when we dealt with radicals and there was division written out, I sort of threw this thing out here and I said, man, we're going to have to do this thing called rationalizing, and it's kind of annoying. And when we're working with it with radicals, right, like we were, it's kind of silly. Like we don't really need that tool for that purpose. But we do need it here, okay? So as we're taking a look at this, we're going to employ the same strategies that we did before where we talked about conjugates. It's always the conjugate of the denominator. So what is the conjugate of this denominator, 1 plus 4i? Yeah, works the same way. It's 1 minus 4i. 1 minus 4i on top. We'll get to the top second because it's the harder one. The denominator, of course, when we multiply conjugates, the whole point is that the inner and the outer terms add to 0. It's always why we did it. Always. So I don't need to do the inner and the outer terms. I really just need to do the first terms, which here would give me a 1, and the last terms, which here would give me a negative 16i squared. Why is this helpful? Because I squared is negative 1, and my denominator becomes simply the number 17. Okay? So let me go back and finish the numerator, and then I'll clean up the denominator a bit more. As always, I actually have to do the full multiplication out of the numerator, first, outer, inner, last. So first terms is 2. Let's see, outer terms would be negative 8i. Inner terms is negative 3i. And my last terms is positive 12i squared. Are all those pieces okay? I think I caught them all right. These two pieces, of course, add together, and these I squareds, in effect, just change the sign in front of the coefficient. So instead of this being positive 12i squared, it's going to be negative 12. And instead of this being negative 16i squared, it's going to be positive 16. So I really have 2 at the beginning, minus 11i, and then I have minus 12 on top, and I have 1 plus 16 on bottom. So this is negative 10 minus 11i on top, if I put the real number part at the beginning, over 17. Again, I should not have any i's in the denominator, right? That's why I did the conjugate business. And I shouldn't have any powers of I when I'm done either. Now, I'm fine with you leaving your answer like this. If you check the back of the book or other resources, what they might do is they might individually divide each piece by the 17. Like this. And the reason they might do that is because technically then, that's in A plus BI form. that's fine. But as far as I'm concerned, it's sort of irrelevant at that point. You've done all the mathematics to combine the pieces in a way that's very understandable, so I'm good with what's in the box, or you can separate them either way. Any questions on that? Okay. I'm going to show you something really cool about powers of I. I didn't think I'd get to it, but we'll do the examples for it mostly next time. So I mentioned we don't have any powers of I, and the reason we don't is because they're always reducible into simply i's or negative ones. That's why. So the first one, of course, is just I. I to the 1 is I. That's what that means. And we've dealt with I squared, and we know it's negative 1. So those are the two we've already seen. The third one, I'd like for you to think about what you can do with I cubed. That is, you can break it apart into I times I squared. Agreed? Sure. But what is I squared? Negative 1. So this is negative 1, which means that this is really just negative I. So I cubed is negative I. We can do the same sort of thing with I to the 4th. I could break it apart into I squared times I squared. What's I squared? Negative 1. And what happens when I multiply negative 1 times negative 1? I get a 1. So that's great for the first 4. But the cool thing that happens is that this pattern, I, negative I, 1, will keep repeating forever with powers of I. And here's how I can show you that that works. I to the 5th is I to the 4th times I. What's I to the 4th? 1. And I'm left with I. I to the 6th. Well, I to the 6th is I to the 4th and I squared. I to the 4th is 1. I squared is negative 1. And I'm got back to negative 1. What do you suppose I to the 7th is? Negative I. And what's I to the 8th? 1. So if we can identify where in this pattern we are, we don't really have to do a whole lot of work to figure out from right here what's going on. We get much of it for free. So I'm going to show you something really cool that you can do to get much of it for free even easier than recognizing the pattern. I to the 19th, I could do this, right? I could write it out till I get to I to the 19th, and it wouldn't take too long. I don't think you want to do it for I to the 77th, though. No, you do not. So let's do what we expect I to the 19th to be. Okay, so I to the 19th can take it apart. You can keep breaking it down. But instead of breaking it down and considering this pattern, it's far easier to look for the number 19 and to figure out where the closest multiple of 4 is. So what's a nearby multiple of 4 to the number 19? 20. But we need it to be smaller, so 16. So I can take the I to the 19th, and I break it apart into I to the 16th, and I would need I cubed, because 16 and 3 is 19, right? Anything that has a power of 4, right here, any power that has a multiple of 4, that's 1, always. If I can get a nearby multiple of 4, it's 1, and I can always get a nearby multiple of 4. And then I cubed, based on my patterns over here, is actually equal to negative I. So I to the 19th is negative I. Okay, so we're considering multiples of 4. Let's try the same thing with 77. First of all, whatever you're looking for has to be even, right? So multiples of 4 are always even. So trying numbers that are even is a good thing to try. So you might try 76, and if 76 doesn't work, you jump back 2 more and you try 72. Does 76 work? Is 76 divisible by 4? Somebody grab a calculator, tell us. Does 76 divide by 4? 19, so it does, yes? So if it divides by 4, it means I'm going to use that value. So 76, and then I need one more of them to get 77, right? So I break the 77 into 76 plus 1. I to the 76, because 76 is a multiple of 4, is 1, which means this is I. 9 requires more work because it's a negative exponent. We've dealt with negative exponents and we've put them in the denominators, right? Like that. So that's what we have to do here. I already know what I to the 5th is. It's on my board at the moment, so I already know that it's 1. That it's I, excuse me. So this is the same as 1 over I. And it's really tempting to leave it there, but you can't. Why not? I is like radicals, right? So we don't leave radicals, we don't leave i's in denominators. Yeah, it's much like that. So I'm not going to leave the I in the denominator. But I can simply multiply by it just like I would by a radical. Why? Well, because that gives me I squared, and I squared is another number. I know. What is I squared? -1. So this is I over -1. What is I divided by -1? Negative I. Now I'd like to show you something else that actually makes that make sense. It's negative I. But I talked about this patterning, right? What is I to the 0? It's 1, because anything to the 0 power is 1. If I went back I to the -1, based on my pattern, this should be negative I. And if I did I to the -2, based on my pattern, this should be a -1. And we could go all the way back up to I to the -5, right? The pattern goes the other direction just as well. So there is a patterning that goes continuum from positives to negatives through the integers. And we can think about it from that perspective too. All right, so we will pause there on complex numbers for today. This assignment will not be due till next Tuesday.